Okay, in this problem, we're going to talk about how high a roller coaster must start off in order to make it all the way around the loop. So the higher the roller coaster is on the hill, the more potential energy it has. So once it goes down the hill, the potential energy is then transformed into kinetic energy. And there's a key point right here that says the first hill on a roller coaster must be higher than the rest of the hills after the hills or loops. So in order for this to go all the way around here, it must be high. The first hill must be higher than this actual loop. So that means if it wasn't higher, then it would actually go around the circle and come at a certain point around here and actually fall down. So the centripetal acceleration has to be greater than or equal to the gravity, which is when it comes down here, it's pushing downward. It has to be greater than the gravity so that it can go all the way around. So the centripetal acceleration is either greater than or equal to the gravity. The centripetal acceleration is equal to v squared over r. So if you substitute this in for a centripetal acceleration, you get v squared over r equals g. And if you solve for v, you have the square root, v is equal to the square root of r times g. Now to find the height that you need for the people to make it all the way around this loop right here, you do the conservation of energy. So the conservation of energy, the total energy at this point must be equal to the total energy at this point. Now here you just have at the first point, 1, you just have potential energy because it's not moving, so there's no kinetic energy. At this point, you have potential energy and kinetic energy. So now we're going to look for H. So for here at point 2, you have the height is actually 2r. This is the radius of the circle, but the height of the actual circle is 2r. So we substitute that in for H on the right side, and we substitute and we cancel all the m's out because they're a factor on both sides, and we substitute v in for square root of rg, which is right here, and then we square the square root of rg, and we just get gh equals g times 2r plus 1/2 rg. G is a factor of both, so we can cancel those two out. So we're left with h equals 2r plus 1/2 r, which h is equal to 2.5 r. So the height, when it first starts off, it has to be greater than or equal to 2.5 times the radius of the circle that you want it to go around. If it's anything less than that, it'll come to a stop and fall straight down.
Friction. The main cause of the energy leaks in the system is because of friction. And it's also the reason why mechanical energy is not fully conserved. Between the train and its tracks, and between the train and the air, there's friction. Since we know the energy leaks are caused by friction, the successive hill and loops on the coaster must be shorter than the hills before. If it's not shorter, then they won't have enough energy to make it all the way around. Friction.
Hey there, Professor Storr. As earlier my friends discussed about kinetic energy, potential energy, and friction, I'm just going to give you a little brief over of the roller coaster here. It's the energy transformation from potential energy to kinetic energy. At a certain height, when a roller coaster is moving, it has potential energy, and when it converts, it starts to go down, and the gravitational acceleration starts to pull it down. The potential energy converts into kinetic energy. And when it starts to go and do the whole movement for the loop, inside the loop, the roller coaster has the kinetic energy and the potential energy, where the centripetal acceleration is equal to the gravitational acceleration. After finishing the loop, we have this kinetic energy pushing this roller coaster towards this height. But due to the force of friction, the kinetic energy starts to go lower and lower, and right after reaching at this point, this kinetic energy converts into potential energy. And that's pretty much it. Thank you.
So now I'm gonna explain all the concepts that we learned before into this one problem. So we're gonna solve this problem right here. It says a cart slides down a ramp without friction around the loop. The cart is released from the height of 16.7 meters from the bottom of the loop, which has a radius of 5 meters. So first part, we're gonna try to solve for the speed at point A, which is over here. So we're gonna find the speed over here, the velocity. And for part 2, we're gonna determine the normal force at point A if the cart has a mass of 8 kilograms. So now we go here. What we know, what is given is the mass, the 8 grams. We can convert it into 0.008 kilograms. The radius of the loop is 5 meters, as you can see right here. It's 5 meters, and the height is 16.7 meters from the bottom. We know that the gravity is 9.8 meters per second squared. We also know that the conservation of energy law is kinetic initial plus the potential initial, which is equal to the kinetic final plus the potential final. We also know that the centripetal force is the sum of all the radial forces. It's all centripetal force is also the mass times the velocity squared over the radius. We can see that. So the cart starts from here, it goes down through the loop, and then over here. So we want to find the velocity at point A. So we go here. The conservation of energy, as I said before, kinetic initial plus potential initial is equal to the kinetic final plus the potential final. So the kinetic energy at the top of the roller coaster is going to be 0 because the cart is not moving at this point. So all the energy over here is the potential energy, which is over here on the top, because the cart is not moving. As it goes down, the kinetic energy comes into play. So in that case, we know that the kinetic energy initial is going to be 0, so we can cross that out. The potential energy is mass times gravity times the height, which is equal to the kinetic final. Kinetic final, in this case, there is no friction, so we know that whatever we start off over here has to be the same energy over here. So kinetic final, which is mv squared over 2, plus we have to account for the point A over here, plus mass times gravity times 2 times the radius. Solving for velocity, we get v equals to square root of 2 times gravity, the height minus 2 times the radius. When we solve, we get a velocity of 11.45 meters per second squared. Moving on to part 2. In this case, the centripetal force is equal to the gravitational force plus the normal force. So this is the centripetal force is equal to gravitational force plus the normal force. Solving for the normal force, we have Fn equal to Fc minus mg, because we're looking for the normal force. And so we know that Fc is also equal to m times v squared over r. We wrote that down there in the given, minus the gravitational force, which is mg, mass times gravity. So we come here, we plug in all the numbers. For mass is 0.008 times this is the velocity, 11, which we got from the other part 1, and we square that, over the radius, which was 5 meters, we can factor out the masses. 0.8 from here and 0.8 from here. We can factor that, and then we get an answer of, well, if we factor this, then it's going to go away, but Fn is equal to 0.1317.2, 0.131712 newtons.
Height. What the hell is wrong? When you drop the ball from a specific height, the potential energy is max. Simultaneously.
And this one stopped.
Now go ahead and throw it. Maybe. I guess I'm ready to go home now.
This is a replica of a roller coaster that we've made. At the highest point of the roller coaster, the potential energy is maximum. And what causes the ball to drop is gravitational pull. Once the ball is dropped, the potential energy is converted into kinetic energy.
Right. According to the law of conservation of energy, the total initial energy should equal to the total final energy, but here it's not equal because we have a work done by the friction, which is the energy loss, which is the energy initial minus the energy final. Right, in this loop, the centripetal force should be more than the gravity, which will cause the marble to move from here to there without falling down.